using Excel, right? And during that lab, we discussed a little bit of beyond the data analysis, mainly about the propagation of errors, right? So what is the error of one single measurement? If you have many measurements, how you get the average? And if you get the average, then the error no longer just a simple instrumental error, how to get the mean deviation and things like that, right? So now this lab, what we try to do, basically, if it is in-class lab, we're gonna use a little bit of more accurate instrument to measure certain measurements. For example, if you measure a length by using a meter ruler, accuracy of the meter ruler is about 1 millimeter. Uncertainty of the error of the measurement is about half the millimeter, that is 0.5 millimeters, right? So you can't definitely measure anything beyond that by using the meter ruler, right? But if you want to measure something extremely thin, something extremely small, for example, let's say I want to measure diameter of very thin copper wire. So usually those diameters are about like 0.2 millimeters, 0.4 millimeters, things like that. There's no way you can measure such a measurement by using meter rule. It's impossible. You can't measure that. Because of that, what people done over the years, people produce a more accurate instrument to measure the same kind of length measurement. So the two instruments we're going to take a look today in this lab. So the only problem with that, this lab is mainly focused about the density calculation at the end. You know, density is volume, mass or volume, right? But that calculation is very simple. But what is really more focused in this lab is how to use those instruments. Now, when it comes to how to use those instruments, unfortunately, this semester we don't have this physical ability to use them, right? You guys can't really physically use them instrument. Because of that, we're going to rely on the simulations. So two simulation we're going to use today. One is for the instrument called the Vernier caliper. Some of you might came across in your high school level. And the other instrument is called the Micrometer screw gauge. So the both of these instruments can be used to measure very smaller measurements such as 0.1 millimeter, 0.01 millimeter, and then sometime down to 0.001 level of millimeter accuracy. And the idea is that these two instruments are exactly look like this. If you have it physically, it's about like 6, maybe 5 inches in length or 6 inches maximum. And then this is about maybe 1 to 2 inches right here, what we call the jaws. And then what's different in this is this instrument has a meter ruler scale. This is scale right here, you see, that is a meter ruler scale. This 1, 2, 3, those numbers are actually centimeters. Top right here is actually inches scale. It can go down to 6 inches, but we're not interested in that scale at all. Hold this rod right here called the main scale, okay? And what we're interested is the SI unit, right? This is the SI unit, centimeter, and then in between each centimeter, you will see another small black line. So those are millimeter line, right? So this is millimeter centimeter scale in our SI units. And the important difference compared to the meter ruler, now you have a smaller unit right here, another scale, what we call the sliding scale or the Vernier scale. So by using Vernier scale, actually you can go far beyond the accuracy of the meter ruler, depending on how this gadget is made. Sometime today we're going to use 0.1 millimeter accuracy, but there are Vernier calipers you can go down to 0.01 level of accuracy. That means 1 over 100 of the millimeter, which is so accurate. Okay. So now to get the better understanding about this instrument, so let's go into the simulator. You will scroll down to page number 5. Then you will get a link right here. Just click on that link. Then it will bring you into a simulator page. Okay. So that's a simulator we are planning on using today's class. One of the simulator, we actually going to use 3. Okay. All 3 come from this same website. So if it is working fine on your side, technically should not have any problem. Otherwise, let me know. Should work in any web browser without any problem. Usually you don't need any specific things to run this. These are run on the web browser directly without any problem. Anybody have any difficulty getting into this simulator? Okay, seems to be there's no problem, seems to be working fine. Okay, now let's take a look how to use this gadget, right? So that's what is really important. Now, if you take a look this gadget, there's a couple of things. Now, this line right here is the centimeter millimeter scale. That is our main scale, similar to your meter ruler. And I can go down to directly 0.5 millimeter level by using this scale itself, right? Then there's a sliding scale. Now, let's say other items too. Now you can see this part right here, which is actually called the outer jaws. This is called the inner jaws. And then if you click on here, you can see the sliding scale. You can take it out and then bring it in. See that? So if you're using this instrument in class, so that's what exactly you're going to do. You're going to open this little bit and then bring the object you want to measure and then place it here and then close the jaw and then read the measurement. Now let's start directly measuring an instrument, measuring an item. Let's say I would like to measure the length of this iron block, right? So on your left hand side, there are a couple of selections, right? Just click on the iron block. Okay, so just click on that iron block, then it should come into automatically one side touching this outer jaws. And then you can see now the sliding scale is open. So to take the readings, you have to place the object like this and then bring the sliding scale all the way until it touches the object other side. When it touches the other side, now it is ready to take the reading, right? So all we have to do now, read this reading right here. Now, when we're talking about reading, we are not reading anything here, right? You can see this jaws right here. This jaw is starting right here. That is not our reading place. Our reading place is exactly where's this line on the sliding scale. You see a couple of lines, right? About 10 lines on the sliding scale. Those are called the Vernier scale, right? So that is actually, you can see zoom in version on your top right hand side right here. A zoom in version. That's the place where we take in the reading, okay? So we close it whenever it touches the object. Then we go and start reading right here. Wherever Vernier scale is starting, that lines, right? So this is our starting point. So how are we going to read this now? We have two different scale, right? One is main scale right here. These numbers represent centimeters, which mean each of this is small number, represent a millimeter. And then you have a scale, which we call the Vernier scale. You have two scale, you have to read the both. First, we're going to read the main scale. To read the main scale, what we're going to do, you're going to go and find where is the Vernier scale starting point. This is the Vernier scale starting point. Let me zoom in there. Now, if you take a look at zoom in area, so this gray color line right here, that's the Vernier scale 0 line. So you first figure out where it is. Relative to that point, you read the closest right line from the top scale, that is the main scale, okay? Relative to the starting point of the gray line, that's the Vernier scale 0. Relative to that point, closest right-hand side line on your main scale. And then read it that in millimeters, okay? Read this line in millimeters. Now this line value is, this is 38 millimeter, 35 millimeter line, 36 millimeter line. So that line value is 36 millimeters in your main scale. Now you go into your lab data sheet And then don't worry about table number 1. I will talk about that in a bit. So we are now working on table number 2. Okay. Dimension measurement of objects by vernier. We are working on iron block, and then we measuring length, and the main scale units we interested to keep millimeters. You will see in a bit why. So the length in the millimeter scale, I'm reading this line, closest line to the left of the 0th starting point of the gray scale, that's the vernier scale. That is 36th line. Okay, you read that. Now you can see, in your case, you might read a different number. Don't write it down my numbers, because I think this simulator has a couple of different versions. Each of you might you getting a different number. Okay, not every one of you getting a different number, but as I understood, they have at least maybe 5-6 different variation of this. Each time you reset the simulator, so this will give you a different length. That's totally okay. But only thing what you have to careful about how to write it down this number. Okay, so that's very important. If you're doing this in class, that numbers directly connected with the density measurement later, so it will be a big problem. But today, these measurements are not directly connected to the density measurement. So because of that, it's not really much important later calculation, but it is still for learning purposes, you have to be really careful, right? How you measure that. Now I have the main scale reading, right? 36 millimeters. Now, if you measure this object, right, this length in the meter ruler, that's what you're going to read. You can't read anything beyond that. So that's the idea of this instrument. Now, you can actually read beyond that. What's the beyond that mean? If you go and take a look, there's a small difference right here. See that? So that is small difference is actually, this is the 36th line of millimeter from the main scale. And then this gray line is actually starting point, 0 of the vernier scale. So what vernier scale can do, it can tell you what is the value of this gap right here. So that's what we actually trying to do. Now you can see immediately what that's the accuracy really, because this is small gap. This is about like maybe 1/4 or 1/3 of millimeters. If you use only centimeter millimeter scale, that is the meter ruler, there's no way you can actually estimate that gap. I can go into half the millimeter by estimation, that's all. Now that's the advantage. Now, how to read that in the vernier scale? It's very simple. What you have to do, you start again this starting point of the gray line, that is 0 of the vernier scale, and then go right hand direction by observing alignment of main scale line to the vernier scale line. So what we're looking into, this slightly greenish or bluish line to the gray line go top of each other. That's what we're looking into, right? You can see each of these two lines are off. But if you go about like line number 4 or maybe line number 5, you can see it close to alignment. It's not perfect. That's okay. That's still the error. Okay. You might not get it perfectly alignment. You have to read whatever you see the first alignment. Okay. If you see this is the best first alignment, you read that value right here. Value means this number. What this number means, this is 0, 1, 2, 3. Follow that? So that is a third line on my gray scale. That is a vernier scale. So which means just the value of that line, right? Number of that line. That is a 3. Third line of the gray scale. Now all you have to do, that line has to have a unit, right? You have to convert this into unit. That is actually what we call the vernier scale unit. Now vernier scale units generally given in this instrument. If you have this physically other side of the instrument, if you turn around, that is written, or that instrument come in the box or the container that has the least count, right? Generally, or there's another way actually we can find even least count by just observing that. Now in this instrument, least count means the smallest possible value you can measure. So that is 0.01 centimeter, which is about 0.1 millimeters, which means value of this each gray line. Value of each gray line is the least possible measurement you can do. That is about 0.1 millimeters, which means this has to multiply This 3 has to be multiplied by 0.1, then you will get the unit here into millimeters. Because always I have to have a unit for all the measurement which I do. Everybody get that? Any question? Then the result gonna be automatically, I have two scale to get the final reading, you have to add them together. It's a very simple addition, 30.3. So I have to add these two, 36.3 in unit of millimeters, okay? In unit of millimeters. Question. Now there is one other question remaining. Now when you write it down the final reading, we have to always mention the accuracy of the measurement, right? You remember last week we discussed very in detail. If you have a meter ruler, least count is about 0.1 millimeters, right? Sorry, 1 millimeters. About 1 millimeters. Least count in SI units mean 1 times 10 to the power -3 in meters, right? Because you take the meter ruler, 1 millimeter multiplied by 10 to the -3, convert the units. Now, 1 cent is the error, right? Or the error of the each measurement is actually half of this measurement if it is analog type instrument, which means error or the uncertainty is about 0.5 times 10 to the power -3 in meters. Now, if I do the same concept for the vernier, least count of our vernier is 0.1 millimeter. Least count in SI units mean 0.1 multiplied by 10 to the power -3 in meters. And the uncertainty of this instrument, this is still an analog instrument, right? It doesn't have a scale to show you the numbers. So it's analog instrument, which means half the least count is the error or the uncertainty, which means this is going to be about 0.05 times 10 to the power -3 in meter, which means if I use that amount of accuracy here, now you can see I am reporting this into first decimal place in millimeter, right? My final answer. But in terms of accuracy of that instrument, I should report down to about 2 decimal places in unit millimeter. So which means this number right here, when you're reporting that, should come down to 2 decimal places, right? You can easily format that, highlight it, right click, format cells, numbers. I should have at least 2 decimal places to represent the accuracy. We talked about those things during the last class, okay? It's still equally valid. Question.
Can you please do that thing again?
Formatting?
Yes, the format.
Yeah, just highlight if you want to format anything, highlight it, click and drag, and then right click, format cells. Then we interested to see like 2 decimal places, click on numbers. Then in here, 2 decimal places, and then click OK. All right.
Thank you.
Any other
I got it.
question? Yeah. And if you're using online version of Excel, still I think most of the formatting what I do should match. But later in the semester, when we do graphing and things like that, online version might be slightly different. Okay. I would strongly suggest you to download this whole Microsoft 365. It's free for your laptop. Then it's much easier. All right. So now you know how to measure that. Let's measure other dimension. This is a 3-dimensional object. So which we like to measure the other 2 dimension, the width and thickness. Width, you click on here right here. That's the width, okay. And the same thing, click and drag out to jaw, and then until it connected, then you read this number, right? When you're reading it, you know you're gonna go and start first starting point of the gray line, that's the vernier scale, and then you look to your left hand side, first line closest to that gray starting point, so that is this line. line value, okay, that line value in millimeters. This is 20 millimeter, 21, 22, 23 millimeter line, okay. So which means in millimeters main scale, I have 23. When you go back there, now I need to read the Vernier scale. I'm going to start again from the starting of the gray line and then moving slowly towards right hand side, observing alignment between the gray line to the blue line. Okay. So if you go there, you can see first closest alignment I can see here. Okay. There is an error always. Someone can argue, no, this may be the closest one. That's totally fine. You can read it. There will be 0.01 millimeter of error here. That's totally okay. That's the reading error. If you do this in class, this part actually very small, extremely small, very similar to this much of size. Then technically you can't really read it directly. Sometimes we use a magnifying glass to little bit observe that clearly. Otherwise, always there are going to be a huge reading error when we do this part. Okay, that's totally fine. Nothing to worry. So you see the first closest alignment. I'm going to read this line. That is the sixth line on the gray scale. Sixth line mean multiply by 0.1. That should be 0.6 in millimeters. Then you add these two numbers. If you want to add anything in the Excel, it is here. I did that previously. You click on that cell, right hand side very lower, you will see that green dot. You click on that, drag downward direction. That will do the addition automatically for you, right? You can see that two cells are added up. Okay, question. Okay, so let's read the other dimension, the thickness. Click on the thickness. And you can see object changes automatically. Click and drag the outer jaw until it touches the surface. Then let's go and read this value right here. And in this case, you can see immediately this is number one, that is 10 millimeters. This is 11 millimeter, which is the closest to left, 11 millimeters. And if you go your right hand side on the gray scale, you can see immediately this line is a really good alignment, right? So that is the first line. First line means 1 times 0.1, that is 0.1. So you click and drag this, that will give you the right number with the right significant figures. Not only significant figures, sorry, but we really interested here is actually number of decimal places right here, okay? Because right now we're just reading the values, okay? When you read in the values, what we really interested to represent how much accuracy I can read this instrument, right? So that's what our main interest right now. Significant figure come later when we do the calculation, okay, detailed calculation. Okay, question. Everybody okay with that? Okay, let's read one more instrument, one more item by using this one. So let's read metal cylinder. If you click on the metal cylinder is a cylindrical shape. Because of that, there's only two dimensions, diameter and the length. Okay. So let's read the diameter first. Bring the outer jaws. When it is touched, this will appear. So I just need to read that. To read that, go and start with the 0th of the gray line and towards your left, first line right here, line value 30, 31, 32 in millimeters. I'm reading diameter of metal cylinder, 32 in millimeters. Let's put the unit also here. Be interested millimeters. Now let's read the Vernier scale, starting from 0 gray line. Move your right hand side, observing the alignment. When you reach 6th line right here, you can see very perfect alignment. So that means 6th line. 6th line means 6 multiplied by 0.1. So because of that, it should be 0.6. Unit for the Vernier scale now, millimeters. Unit of the final reading, millimeters. Don't worry about SI units at all when you're reading something. Okay, that's not what we interested when you're reading. What we interested is the real units, what you can directly read in that item, accurate as possible. That's what we interested here on table 2. So we report with the right unit directly coming from the instrument with the right accuracy. Then at the end, when we do any calculation, after we finish the calculation, very end, we're going to convert everything into SI units. Okay. Now you add these two, that's simply 32.6, right? Nothing much to do. However, I have to represent another decimal place to represent the accuracy. Let's format these two cells. Right click, format cell, number with 2 decimal accuracy. Question. Okay, so let's continue then. Let's read the other dimension. That's the length. Click on the length, then the object will change automatically. Bring the outer jaw. After it connected, let's read this one now. The line left to the first gray line right here, that is 4, which means 40 millimeters. Okay, 40 millimeters. And the Vernier scale means starting from the first gray line, go your right hand side observing the alignment. Read the first alignment, okay? Sometime it might be close right here. I'm gonna read this third line right here as the alignment, but technically you can see these two also very similar, but I'm gonna read the first immediate one I see as alignment, okay? I'm gonna read into third line, so which means this is gonna be 0.3. This is going to be then 40.30. Okay, so we have all the dimension done for those two objects. Question? Okay, then let's continue. Now, if you have dimension, you can do certain calculation, right? So the last experiment, the dimension was given, right, on a tabletop, and then you done calculation, perimeter, volume, area, and then so on. So this is exactly the same calculation. There's not much different actually. So we're going to do the volume calculation directly, right? This is a three-dimensional object. Let's calculate the volume. Calculate the volume here. Volume equation is actually given here, right? So the volume I can calculate equal sign. I measured only one time, right? So there's no average or anything in this case. Length times is the star sign, okay? Width times the thickness. And I'm calculating in millimeters, okay? Because of that, this unit right here should be millimeter to the power 3. Now it's millimeter cube, okay? Should be millimeter to the power 3, millimeter cube. Following? And now let's take a look the numbers. Now you can see this is a large number. Whenever we have large numbers, anything like thousands, 100 may be okay. You can leave it without worrying about significant figures, but anything more than hundreds, like 1,000 or beyond, we're not going to leave that number like that. That's bad. So that's why we talk about scientific notation, right? Anytime you see a large number or really small number, we're going to rewrite those numbers in scientific notation. Then you take a look the accuracy or the significant figure. So in this case, what I like to do now, this is a calculated value, length, width, and thickness. Then I'm going to take a look all the numbers here and then leave this number in terms of that significant figure. Okay, how many significant figure I can go? All of these has 4 sig figs. So which means technically I can leave here 4 sig figs. Right click, format cells, scientific notation, 4 sig fig, one number and 3 decimal places. Okay, then totally 4 sig figs. If it is a larger number, that's how you should leave your calculated value. Okay, should not leave it as a as 1,000 of large number. That's really not good. Let's calculate the error too. I'm going to do only this part. This part you have to do yourself, okay? So later, not right now, we're going to continue to the next calculation, but the later for the cylinder, you have to do exactly same calculation yourself. Let's calculate the error. Now, you know, error is depending on the equation which I use. When it comes to the error equation, you know, we're looking into two different rules: addition, subtraction rule, multiplication, division rule, right? So in this equation, all multiplication, so which means I'm going to follow multiplication division rule. So accordingly that, I have to get the fractional error for each variable here, and then square it and add all of them together. And take the square root, multiply by the volume I calculated here. That will give you the error for this calculated value. Let's do that. Equal sign, volume calculated, multiplied by sqrt, that is square root function in our Excel, parentheses, another parentheses, error for the length. Now, error for each of these values depending on one measurement. We did not do any average or anything. Okay, therefore, there are no mean deviation or anything. Error for one measurement is error of the instrument. Error of the instrument is 0.05 in millimeters. I'm still using millimeter units, okay? 0.05 millimeters divided by length itself, close brackets, power 2 plus open brackets, 0.05. Same error for the measurement because same instrument I used there, divide by width and close bracket, power 2 plus open brackets, 0.05 divide by thickness, close brackets, power 2, close outer bracket for the square root, hit enter. So then you will get the error for that calculation. Let me copy paste that to somewhere here. You can refer that as needed, okay? So let me copy into this cell. Get rid of equal sign and then get rid of this equation little bit further away, okay? So that's the equation I use, and then this is the function I use. Okay, make sure when you copy paste this table into your report, I'm not interested in this function here. Okay, let me change that. That's not a good place to leave it. Otherwise, you may get confused later. So let me leave it here. All right. So that is actually how I did the calculation, which is delta V for block. Delta V for the iron block. Okay. So that's the function. And
Professor,
later, yeah,
how do we convert the answer into scientific notation and notation in Excel?
same way, you click on the cell, right click, format cell, scientific. Now I need one number and then 4 decimal places, right? Not really, actually. I can go only 2 decimal places technically. No, I can go only 1 sig fix according to my equation. So which means should do scientific notation without any decimals.
Okay,
5
thank you.
times e to the power 1. Now you can see this is e to the power value, right? This is a really large number. This is 10 to the power 3. As a result of that, you can see error going to be extremely small value, okay? Because why I went to 1 sig fig, the reason is 0.05. That has only 1 sig fix, okay? Good. So your error should be extremely small compared to this. This is in thousands. This is in just tens. Now, same way you have to do this part, okay? I'm not going to do this part, which means for your lab data sheet purposes, tonight when you're submitting, you don't need to worry about completing anything we're not completing now. That's okay. If you don't have time, have another class after this class and then so on. Don't worry about that. You have only few hours before midnight. That's totally fine. You can leave it as it is, but you still submit the data sheet. But do not misunderstand. That doesn't mean that you should leave it open for your lab report, because lab report must be due in a week. By that time, you should be able to complete all of these rest, whatever we skipping, okay? Please make sure you understand that properly. Okay, any other question so far? Anyone else has a question? Okay, then let's continue to next instrument. So now the only disadvantage with this virtual situation, now this measurement not directly proceed into our next part. That's the problem now. If we do in class, then this measurement we directly measuring is actually part of the density calculation later. That's okay. So nothing much to worry. Let's go into next instrument. Now you know how to use this instrument. When it come to next one, it's not really anything new. So it's a very similar instrument, what we call the micrometer screw gauge. There's a little bit of difference, but you know what's now what we're looking into. There's a two scale. This instrument has a linear scale like the same way, millimeter scale, and then there's a circular scale which can rotate. So that's the difference. Let's take a look. What is this? Click on this link right here, micrometer screw gauge. If you click on that, you should get object which is similar to this. Okay. Anybody have any difficulty accessing those web pages? Let me know. Okay. Usually these are working fine, but since these days many thousands of people accessing these websites, sometimes those website can give you an error or something like that. Let me know. I'm using Chrome web browser. Generally, they should work in any web browser without any problem. All right, now let's take a look. Anybody have any problems, difficulty getting into that simulator? Okay, so then let's continue what we looking here. Let's take a look the item itself, right? So the item is slightly different now previously, right? So it has now this curvature area here, and then you can see this part right here is actually called the screw, and then this actually called the stud right here, this end, and the object go in between these two, stud and the screw. And this screw can go in and out. That's why it's called a screw really, right? So because it can go in and out, that in and out motion you can control by using these arrows right here. If you click on this arrow, this part actually called the ratchet. If you click on the ratchet, you can see that is screw going in, right? Up arrow. And then similarly, if you click the down arrow, it can open up. Technically, you can move this in and out by using this barrel right here. That's a circular scale. You can really rotate that scale. That scale going to be rotate around this cylindrical shape object right here. And then this will go in and out. Why we don't use this barrel shape circle here, barrel shaped cylinder here to move this in and out, because that can actually damage this instrument. The reason what going to happen, if you rotate by using this, and if it is fully closed like this one, after it close, you can see immediately after it close, this appear, right? Which means we have to stop. But if you rotating from here, you can actually apply a force and then rotate more and more. As a result of that, what will happen sometime, this circular scale can go in more and then crash in. That will actually create the error that called the zero error. Sometime zero error plays a major role in this instrument. Now let's take a look what the zero error means. Zero error means, now you know the idea, what we're looking into, when this stud is actually connected with the screw, when the screw come and close this gap fully, then this place right here, zero of the main scale should align with the zero of the vernier scale. Then we say it's ready to take the reading. That's where the zero error can happen. If those two zeros are not lining up, there will be a zero error. Let's take a look how that happens. Now on this page number 3, you can see 3 pictures, which you can identify what are the zero errors are. There's 2 types of zero error, right? If there's no zero error, you should see a picture like this one, picture number A, which means zero of your that horizontal line, that is our main scale, should directly align with this zero of the circular scale. If that is not happening, then 2 other type of zero error can happen. So one zero error means zero of the circular scale can be slightly below the main scale zero. Then we say that is a negative zero error. All we have to do, figure out what's the difference between this horizontal, this main line, to the zero line of the circular scale, and then subtract that amount from every reading we measure. Not a big deal, but we have to check that. And the other type of error called the positive zero error. All we have to do again, find how much difference between the zero of the circular scale to the horizontal main line, and then add that into every reading we taking with this instrument. So one is positive zero error, one is negative zero error, one is no zero error at all. Which means before we take any measurement with this particular item, which we call the micrometer screw gauge, you have to check that. So let's check that. So now I close this one fully. You're not going to see exactly what I say because they have a couple of versions again. You might see slightly different, but you have to read what you see, okay? Now you can see zero is this, right? That is the main scale zero. And this is the line which I talking earlier, main horizontal line, this black horizontal line. Now, if there's no zero error, zero of the circular barrel should be on here, right? Cylindrical barrel or the circular scale should be here. Now you can see it's slightly off. It's a positive zero error. And the difference is about 2 lines. So which means this instrument has a zero error already. Let's write it down that on our data table right here. Before we take the reading, let's write it down. There's a zero error. That zero error is, you can just write it down on the top. Zero error, which is equal positive point, positive 2 segment, positive 2 segments, segment line. But each segment line, you see those parts are very similar to the previous instrument. Each segment line is actually called the least count, which means similar to Vernier scale, this is the circular scale. One of this line represent the least count. That least count value usually given in your instrument, in this instrument, which is 0.01 millimeters. Now you can see accuracy is much higher, down to about 100. So my zero error now, 2 times 0.02, which means technically 2 times 0.02 in millimeters, which means 0.02 in millimeters positive. That information I need to proceed with the calculation, right? Any questions so far? Zero error usually going to be fixed for the instrument, right? So which means after I measure once, I don't need to remeasure again since I using the same instrument again and again, right? So let's do a couple of measurements, right? If you want to do any measurement here, all I have to do, go your left-hand side. I'm gonna take the diameter of this lead shot, click on the lead shot, then it will appear here. That's a small circle, right? You can see if you're really doing this measurement yourself in your, if you're really measuring this by yourself, it's going to be a little bit of tough to do these things, right? So now after you place this object right here, all we have to do, click on this ratchet, click the up arrow until it touches the object. As soon as it touches, you can see this zoom in scale appear. So it's ready to take the reading. So that part is very difficult when you do this by hand manually, because as soon as it touches, you have to stop. If not, you actually creating some time error. That's the thing I mentioned earlier. We should not rotate by using this circular scale at all. Let's take this reading now. That part is again the same way like you done earlier. What we're going to do, we're going to first moving on main scale until I meet the circular scale, this front line, okay? So all of these lines are in millimeters. Since we're reading really small numbers here, this 5 means 5 millimeters, okay? 5 millimeter line is actually toward your left of starting from this circular scale front line. So I'm going to read into 5 millimeter line, okay? So which means the lead short main scale is 5 and the unit is actually millimeters. Now you know rest is actually this part, right? You see that this gap is the red. That gap I can read by using this circular scale, similar to the previous, but there are slight differences here, okay? Now on this one is actually much easier to read than the previous because all we have to do to read the circular scale, what we're going to do, we're going to observe this horizontal main line. You see this midline, horizontal main line, and then check the number exactly on top of that main line or the closest line, okay? So in this case, you can see this line on the circular scale is aligning with the main line. So I need that number. So that number value is, that line number is, this is 70, this is 80. So which means this is 75, this line is 76th line. So that line value is 76. But that 76 must be converted into the right unit. To convert it into right unit, all you have to do, you know, each of the line on the circular scale is 0.01. You multiply 76 by 0.01. Then you have the right units, that is millimeters. Now you add these two together, that your final answer 5.76 in unit millimeters. Question. Okay, then let's go and take a look couple of things on table number 1. You remember you have to complete micrometer screw gauge. Least count is 0.01 in millimeter. Now you can see how the accuracy increases, right? So you can see meter stick only 1 millimeter, micro caliper 0.1 millimeter, micrometer screw gauge 0.01 millimeters, right? Accuracy increasing as you go downward direction, right? Now the least count in SI units, 0.01 times 10 to the power minus 3 meters. Now uncertainty on SI units, uncertainty is half the least count, which means 0.005 times 10 to the power minus 3 in meters. Now you can see immediately, if I want to report any measurement on micrometer screw gauge, I have to report down to 3 decimal places in millimeters. So which means this reading is not now accurate. So I read only down to 2, but technically I can represent the uncertainty of the instrument. So which means I have to reformat this cell, right click, format cells, number, down to 3 decimal places. Then I have the right accuracy because all measured values you have to write with the correct accuracy. But when you do calculation, then you can take a look the significant figures. When you're measuring, we are not interested sig figs at all. What we interested is the accuracy of the instrument. Okay. Good. Any question? Okay. Now this is a spherical three-dimensional sphere, which means only one dimension, right? So that dimension is the diameter. So we don't need to worry about at all measuring anything else. Instead, let's measure different thing. Let's measure thin wire. If you go into the selection tool right here, it says select an object. And if you click on that, before that you have to reset the simulator, click on the object, then you can see you can measure different item, but we are not measuring all of them. We're going to measure at least one other object. Click on the wire. While length is given here, we can't measure length by using this one, but the diameter we can measure by using this. So those are the type of measurement we actually going to measure by using this. For example, the small wire diameter or a small spherical shape object diameter, things like that. Okay. Or maybe very thin sheet thickness, things like that you can measure by using this instrument. Again, the same thing, click on the up arrow, until it reach and then connected with the object. As soon as it's connected, you can see this zoom in picture appear. So then we are ready to take the measurement. You know what we're reading is actually go to the starting point, this front edge of the circular scale. Then you're going to read towards your left what is the value of the main scale. Now in your main scale is 0. It's in 0, right? Whatever the left to this starting point. So which means main scale doesn't have anything in terms of diameter. And I'm using still millimeters. Okay. And let's go back here. And I need the length. So the length is actually 5 centimeters that we need later. And also then take a look what's the circular scale, right? To read the circular scale reading, all we have to do, observe the horizontal black line. Relative to that black line, what line is exactly on top of that, we're going to read that. On circular scale, that is this line. That line value is 75. So which means multiply by 0.01, that's going to be about 0.75. Which means final reading of this diameter is 0.750 because you know I have to add the third decimal place. Format cell, number, third decimal place, because then only I can represent accuracy correctly, okay? But the length on the other hand is given. So I can't really do anything about it, but let's assume that is a large length, right? 5 centimeter. Let's assume that measured by the meter ruler, right? If it is measured by the meter ruler, how much accuracy I can go? Only 1 decimal place in millimeters. So which means if I measure this in millimeters, that is 50 millimeters because 5 centimeter. There's no any circular scale, right? So I can just get rid of that. Don't write it down anything. You can say just no. And the final reading is just 50 millimeters. However, you have to write it down that with at least 1 decimal place. The reason if I measure that by meter ruler, I should have to have 1 decimal place in millimeters. Okay. Then let's add the units also. All of these in millimeters. Let's write it down. The length is measured in meter ruler and the diameter is the only one measured in micro screw gauge. Okay, micrometer screw gauge. Question. No questions? Okay, so let's take a look then. One calculation for this one too. There's 2 extra calculation, but you should do them yourself, some of them. So I skip this part, but make sure all of them are completed for when you do the report next week. Okay. So this one also I'm going to skip the wire, but let's calculate this one for the lead short. That is a volume, right? So the equation for volume. So if you don't know any of those things, don't worry about. Just go into your lab manual. So the everything is there. Okay. So you just scroll up and then go down slowly. So all the equations should be given here. Density, volume, and the volume cross-section area of the cylinder, you need that. Volume of the cylinder, you need that. And the volume of the sphere, you need that. Pi d square divided by 6. Generally, it's going to be pi r square, but this is actually diameter we measuring. Because of that, this formula is written to the correct equation with the diameter. Okay, that is why it is pi d cube divided by 6. So which means I can calculate this easily. You have to write it down, that equation, right? If you want to write down any equation, so you have to always use insert, symbols, equation, and it will appear anywhere, doesn't matter, but you can format it nicely. So I need division there. On the top, I need pi. You can select that on this selection tool here. I need pi, and then I need diameter to the power 3, right? So which means I need this selection tool to show me this sign right here. So which means I can do superscript easily, right? So which means I need diameter to the power 3 and then divide by 6. So you can do this editing very easily and then click and drag that equation anywhere you need to have. Because if you input the equation, that not automatically going into the cell whatever you need it, okay? Yeah, so all you have to do, click anywhere, then insert symbols, equation, then this box will appear. Doesn't matter where it is, just start writing, okay? Because we're gonna click and drag anyway. I need this division because there's a division in my equation, right? And then on the top, I need pi. Those Greek letters you can find here. You can change even to different symbols, pi. And then I need superscript. So if you want to get the superscript, you have to select these symbols right here. So that can do d to the power 3. And the denominator, you need 6. So if that is not there, I don't know why. If you use in the online version, this is going to be different. Okay. So usually if you input, if you do insert symbols equation, that column automatically appear. Otherwise, you will see this equation term there. Just click on that. If that is not clicked, then you're not going to see that. So every time when you do something new, this menu bar automatically changes. Okay, now you should be on equation menu bar. If you do in online, then this may be completely different there, or maybe you cannot do this at all with the online version. That I don't know. You need to take a look that, and you can ask me later. Still, you have the same problem. Okay. Those are just editing should not be any trouble. You have enough time because those are not important. These editing not important when you're doing the data sheet tonight, but those are important when you do the lab report. Okay, whenever you need to do the equation, you have to write in this format. Don't just type the format like pi times d to the power cube divide by 6. That's very ugly and the formatting is very bad. In the first lab or second, I might not reduce point, but later in the semester, that may be a reason for the point reduction. So this is not just, I mean, think about that, right? So this is not just you trying to learn physics itself. This is actually far beyond that. This is not really learning about these numbers, symbols, and then anything. This is actually a skill you gaining. That is skill you gain, gonna remaining with you forever. That's why I always telling you that think about that approach, then you have a motivation to learn this. This is not just to pass this class. Whatever you learn, this report writing, things like that, gonna remaining with you forever. That will be a very good skill to have anyway, okay? And these are not really difficult at all. You Google it, there's millions of YouTube videos, you can learn these are very easily. Okay, anybody have any other question?
If I'm not mistaken, you mentioned that we're skipping some tables on here, like that we
We are
don't have
not
to submit.
we are not skipping. See that part only you hear very clearly, right? So that is very normal for a student. If a professor says we're going to skip this, we don't need this one, okay, that's fine. Nothing to worry. Nothing you can skip in terms of lab report. Okay. When it comes to this kind of work, you should not think about what to skip. Instead, you should think about to complete everything by tonight, midnight. So what I say is, make sure you hear it very clearly. If not, ask me again.
Okay.
I skip this part. Anything I skip during this time, it is not required for the lab data sheet purposes. There's two different things you submitting. Lab data sheet must submit by tonight, midnight, okay? When you do that, you can skip that. But when you do the lab report, next week, everything must be completed. You get that idea? Everything must be completed, okay? So that is a general comment I usually hear from the student. That term is very dangerous. Probably I should not use. The term is skipping. Okay. Anybody have any other question? Okay, I even wrote it here. Okay, do not send me a couple of many emails after the class done. Can I skip this one or that one? Generally, I will not respond an email after about like 6 or 7 p.m. Okay, until tomorrow. And make sure I will highlight this one too. For data sheet tonight, you can skip these lines if you want to. I will not recommend it anyway. But for the lab report, you must complete all. Okay. All right, so let's continue to next calculation for this one. This also I'm going to skip this line, okay? Next line, but let's calculate this. Volume equal pi 3.114. There's a pi command, you can use that too. So I'm going to use just 3.14. Multiply by d to the power cube. This is the diameter which I measure here. Power is actually shift and number 6 cube. Divide by number 6. So that's actually volume. Remember what volume we're talking about here, unit millimeter to the power cube. So that's very important because this calculation we do in for very small object, but you see large numbers. The reason we are using the smaller unit, okay, that's why. Now I need to take a look the sig fig, right? Because I did a calculation. So if I take a look the sig figs, how many sig fig I can go here? Now only one measurement. That measurement has 4 sig fig. Technically, I can go 4 sig fig there because there's no other measurement, other measured values at all. Number 6 and number 5, number pi is actually just numbers. Those are not measured values. Okay. In terms of sig fig, what we interested in terms of sig fig, what we really interested is measured values. Okay. Measured values, not any numbers in the equation. Okay, not any numbers in your equation. Make sense? Make sure you really follow those things, otherwise at the end you might get a completely different answer accordingly. Okay, which means right here, right click, reformat numbers. I can go either number format for sig fig or scientific, one number and then the 3 decimal places. Okay, either way is fine there. It's a little bit of large number. I'm going to write it in scientific format. Let's calculate the delta V. Unit going to be millimeter cube again. Millimeter cube again. And let's calculate this equal sign. So I need the volume calculated here. Multiply by 3. Multiply by parentheses error or the error of this measured value diameter, that is the uncertainty of the micrometer screw gauge, 0.005 in millimeter, right? I need in millimeter, okay, 0.005 divide by diameter itself. There's no average value or anything, close brackets. So that is the error of the measurement, which is about 2.6 but 10 to the negative 1. So the error is about like 0.026. Still, now in this case, how many sig figs I can go? I can't go that many, I can go only one. So I'm going to reformat this, right click, reformat, scientific, I can go only one sig fig. Okay. That means about like 0.3, that's the error, right? You can see the error is extremely small compared to this number because this is a really, really large number. Okay, question. All right, so this part I let you to try, right? So some of you might do it today, but if you don't have time, that's okay. But make sure in terms of lab report, make sure you complete everything. If not, always reach out and ask, okay? If you have any difficulty with any of these formulas, how to work with them, how to manipulate, if you don't know anything, just reach out and ask. Idea is that don't use the calculator for any of these because I want you to include all of these function. Okay, let me copy paste this function too. Collect this function as you do the calculation nearby that table. Okay, this is now delta V for the lead shot, right? For the lead shot. Now that's the function I use. Collect this function as the calculation progress. Then when you do your discussion and you need to call this function, and then when you have to write the discussion for each table, right? So each table, few sentences. That means how many table this has. This has 10 tables, so you have to write 10 paragraph in your discussion section. Few sentence, not much, okay? You can fit maybe into one page or maybe 1.5 a page maximum. So the about few sentence per each table. When you're talking about, that's what you're talking about. What you did, how you did that calculation, what's the error, and those are the discussion you do, right? At that time, you have to bring this, you have to call this. That you can directly use this function as it is, or you can copy paste this into appendix C as a series of formulas, then you can call there. I used to calculate error of this volume of the wire by using equation number 6 shown in appendix C. So that's how you're going to do your discussion, okay? All right, question. Okay, seems to be there's no questions. So let's continue then. Let's take a look then. Now, if you calculate anything like this volume and then volume error and then so on, you remember last experiment we discussed when you have to report it properly, right? When you're reporting it properly, now what we have to do, we have to write it down in scientific format with correct accuracy, right? Now, when you're reporting here, you can see there's a table. It says report iron block, metal cylinder, lead shot, thin wire. All of the objects we measured here, those are the 4 objects we measured. And then it says volume calculated without rounding and then volume calculated with rounding, which means technically that is what it's mean, right? You have to use the non-rounded value and the rounded value, which means technically here, when I do these numbers, I don't need to really round it exact significant figure with the correct accuracy. Instead, you can actually leave it couple of decimal places more here. Then you know that's the right number we're getting with the calculation. When you come into this table, round it properly. Write it down first non-rounded value with little bit of few more significant figures and then rounded value with correct significant figure. Let's do that for practice. These numbers I'm gonna round it to little bit higher significant figure. I can have 4, but I'm gonna go to more decimal places. I'm going to leave it 5. If you see this hashtag, which mean technically that width is not enough. Okay, you just need to click on this very top and then sideway click and drag, give a little bit of higher higher width to that cell. That will show up the number. Okay, this also I'm going to leave it a little bit of higher sig figs. So let's do like 3 more decimal places, but I can't have that many. Okay, leave it like that. This also leave it higher. Don't round it right now. Leave it more number of significant figures, as many as you needed, but you don't need to leave like, 10 of significant figures. Just, 1 or 2 than what you expecting. Just leave it like that. Then let's write it down this. Right here, you need to write it down this format, right? In right SI units, this format. SI unit is actually meter cube for the volume, right? That's the right SI unit, but I measured everything into millimeter cube, which means what I have to do, write it down my read value and then convert millimeter cube into meter cube. Let's take a look what the conversion. 1 millimeter is equal 10 to the power minus 3 meters, right? So if you cube one side, 1 millimeter cube, which is equal 10 to the negative 3 has to cube, right? So which means 10 to the minus 9 meter cube. Follow that? That's the conversion, okay? All of these highlighted areas not to include into your report or anything, that is only for your learning purposes, okay? So that's the conversion, which means I can just directly write it down the number which I calculated earlier, parentheses, multiply by 10 to the negative 9, I will get the right answer. So that one way to do that problem. Or I can bring these all numbers and then multiply by 10 to the negative 9 and then correct with the right significant figures and the right SI units. Let's write it down this first. So now I'm going to write it down the iron block. I need to insert equation anywhere, doesn't matter. Parentheses, let's write it down this number, volume of the iron block, 9.50, little bit higher sig fig, okay, 50915, plus or minus. That's why I'm using insert, otherwise you can't use that symbol, plus or minus, okay. And then the error calculated for that one, this is e to the power minus 3, which means you can use e positive 3, e positive 0, 3, and then plus or minus. And then I have 4.911 e positive 1, positive 0, 1, close brackets, and then unit is now millimeter cube, okay. So that's my unit. I can leave it like that, or I can write the unit nicely if I use this command right here. Then I can use millimeter here and the superscript cube. So that's our number which we're looking into. Then you have to click and drag. Yeah, it should go is right here. If you don't have enough cell space, all you have to do is click and drag this one to give more space, okay. And also whenever you copy paste the table into your lab report, make sure the tables are not go off the Word file. So that should be rearranged again, okay. Now that is my number in millimeter cube, but that is not what I needed. I need the meter cube, right? Which means I have to go here and then multiply this number by 10 to the negative 9. Power 10 to the negative 9, then you will get this in meter cube, or you can do multiply, or you can say just E minus 0.9. Follow that? So you can do any way you like, doesn't matter, but make sure you do exactly correct answer at the end, okay? I will rearrange this one a little bit more because I need more space. Okay. Now it's good. Question. You can do either 10 to the power here or maybe E with the positive negative value. That means the 10 to the power value. Okay. Let me show you that also. That might be nice if you write this way. Parentheses 9.5, 9.5, 0915, and then times 10 to the power you can do with this function, 10 to the power positive 3. That is looks nice then, right? That's why. Format. Okay. And then I need plus or minus. Then I have 4.911. Then multiply 10 to the power value you can do nicely with this formatting. That is 10 to the power only 1. Then you close brackets. Then multiply 10 to the power again, this function. Now you need 10 to the power minus 9. And then you need meter cube. Then you can do that also nicely with that formatting. Meter cube, okay. You can see what's the different the way you write, right? See that? So the second one looks very nice compared to first one. So I'm going to use this one. But you can use E without any problem. That okay, that standard way of writing. But that looks very nice, the formatting and everything. Okay, question. Okay, now let's write it down the same thing with the rounding, right? All you have to do, copy paste that and into here. Now I have to round it, right? When I round it, you go back and take a look how many sig fig I can have. So this one I calculated iron block, all 4 sig fig, which means all the numbers should have only 4 sig, right? Now let's round it this. Now if I rounded into 4, 1, 2, 3, 4, which means these two should not be there. And to this one error, I can round it into 1. So which means this I should round it into actually 5. Okay. Everybody get that? How to write it down both non-rounding and rounding. Now you can see that's why in the exam question I like to see this number first always non-rounded value, okay, because sometimes we adding a lot of error purposely by rounding. So that's something very important when you do the exam question. Make sure you follow non-rounded answer orders. Okay. Okay, guys. So I think we should take a quick break right now. So it's about 4:40. Let's take about like 8-9 minutes, and then we'll continue the other half of the lab. Okay. So next half is actually fairly straightforward and easy. If you have any question, please ask. Let's continue. Anybody have any question, any concern so far? Okay, so let's take a look then the other part of the, I'm gonna leave you these sections you to complete, okay? So you just need to write it down, this information, after you complete these two table, okay? So after you complete table, you have all 4 items, volume properly measured, and then you just need to write it down. Make sure when you do these 2 tables, do all the calculation little bit of higher decimal places than what it should be in terms of sig figs. Don't round it there, and then instead round it after you reach this table, okay, table number 7, because it is specifically asking you to do non-rounded value and the rounded value, okay. So if you round it earlier, that will be a problem when you reach this place.
Professor.
Yeah, what's up?
So once we do the rounded value on table 7, on table 3, should we leave it with all those sig figs or?
Yeah, I just leave it like that. Yeah.
Okay.
Because earlier I forgot actually it is asking here. That's why I try to round it into the right sig fig. Since it is asking here, I would suggest leave it.
Okay, thank you.
Yeah. Okay, so I think this part you can complete, right? It's not big deal. It's the same thing, just rewriting. And try to use this nice formatting with the equation editor. Otherwise, you are writing here. If you write this long equation without equation editor, just by general writing, it's gonna be looks very bad. Okay, editing gonna be looks very bad.
Professor, I'm
Yeah,
not able to get the equation editor, as you said, on my version.
I have
Like,
no idea why it is not there. You can maybe Google
can
it.
you show me, like, where you did it?
Oh, it
I
is in
didn't see
here.
it.
Insert, and then new. A menu bar will appear, and then toward your very right hand side, very end, you should see a symbol.
Mm-hmm.
Then you click on that. Inside there, you will see a equation and the symbol too. Just click on the equation.
I only see the symbol button. I'm gonna figure it out later myself.
Yeah, just search on the maybe you can try help and later, and
Okay.
then click on help here and then search equation editor and then see what it's given up. Usually, if you have a laptop version that should have equation editor included, there's nothing to download separately. But take a look that if it is impossible, let me know. I can take a look in that too. Okay.
Okay. I'll figure it out myself. Thank you.
Okay, yeah, you take your time. Nothing to worry about this. The data sheet submission, don't worry about too much. Okay, just do whatever you can in this table. Just submit it tonight. Even if it is not complete, you're not going to get any point reduction for that. But Make sure by next week, Friday, when you do the lab report, you should have everything done, okay? All right, guys. So anyone else has any question? Okay, so then let's continue to next part. Next part, we're gonna calculate density. Now, if it is in class work, then the earlier calculation, everything we can use here. But since we don't have that ability, we have to do completely this density measurement separately, right? So what we're gonna do for the density measurement, if you go into your lab manual, you know density is mass or volume, not big deal. And then all we need is a simulator to do that. If you scroll down to page number 6, then you will see a new link for the density measurement, right? So click on that, and you should get a new simulator. It also in the same web page should be look like this, like a spring balance hanging there, and then couple of objects on the bottom. I can select any object, I can measure mass, I can measure volume of the object, and then calculate the density. That's the plan, okay? Okay, now we are working on table number 8, mass and density measurement, right? So we have like 5 objects here. I can measure all 5 if I needed, but it's the same measurement again and again. We're not going to measure all 5. Instead, we will measure cylinder and the lock and the stone. Okay, that's the plan. So let's measure mass of the cylinder. Just click on that. It will go and hang on the spring balance. Then you can see zoom in portion appear. So that is our scale. If you take a look this scale, you will see grams on your left hand side, newtons on your right hand side. You know Newton is the weight, mass times the gravitational acceleration. That is not the unit what we interested. We interested the real mass of the object, that is gram here. And then you have to observe the scale, right? If you have a new instrument, you have to observe the scale and then figure out what is the least count. Least count means the value of this is small line. If you take a look, this is 0, this is 25, which means each of this small line is about 5 grams. So which means, let us go to table number 1. And on table number 1, it is asking, what is the least count of the spring balance? That is about 5 grams, right? 5G. And the least count in SI units. SI unit for weight is kilogram, 5 times 10 to the power minus 3 kilogram. And the uncertainty of this balance is going to be half the least count. That means 2.5 times 10 to the power minus 3 kilogram. Now you can see error for this spring balance is very high. Okay, it's about 2.5 gram. If I measure a smaller item, the error is going to be so large. But these objects are fairly heavier. Because of that, that error will not be a big problem at all. Now let's measure this one. To measure that, all we need to do is reading this red arrow, your left hand side scale. Now you can see this red arrow is in between two small lines. This is analog type measurement. Because of that, I can actually estimate in between two lines, right? So this is 150, 155, 160, 165, and then next line is 170, which means I can read in between 167.5. So mass of this object, cylinder, I can read into 167.5. I am using the unit of grams directly. Okay, I'm not going to change anything. Whatever directly can observe, I'm going to use that unit. That's the mass. Question. Okay, now let's measure the volume. Now to measure the volume, what you have to do, let's measure mass of all 3 objects first, then go to volume. That is here. Let's measure the mass of the lock. All you have to do, click on the lock. Lock will go and hang there, and then zoom in version appear. Then let's read this number. 200, 205, 10, 15. This is 20. Red is in between. So I can read 217.5. 217.5, right? Because I can always go down to second at that first decimal place. You remember, error right here in gram, 1 decimal place. Okay. Let's measure its tone. Click on this tone, it will hang there. Then we'll read this number. 50, 55, 60, 65. This is 70, 67.5. 67.5. Okay. Question. All right, now uncertainty of the mass, then we did not measure anything like multiple measurement, average, mean deviation, nothing is needed here. Uncertainty gonna be uncertainty of the direct measurement, which mean if you have one single measurement, uncertainty is uncertainty of the instrument, that is 2.5 gram. So I'm using unit gram here. So the uncertainty gonna be 2.5, 2.5, 2.5. All three is gonna be the same number. Question. Let's measure volume then. So I have to measure volume. If you want to measure volume, you have to select that measurement tool. That gonna be inside right here, left hand side you see there's a selection tool. In that selection tool, you see this top one, select type of the test, change that into volume. Now, to measure the volume in this case, we're not going to do measurement, right? So what we're going to do a method called the Archimedes principle. So don't worry about all the theory behind it. What we need is the basic idea of Archimedes principle. So what he figured out is that if you have an object and then if you submerge the object into a fluid, there will be certain amount of fluid displaced. So what he figured out is that the amount of fluid displaced must be equal to the volume of the object. That's it. Very simple concept, but very useful to measure the volume. What we're going to do, you can see there's a container with the water. We're going to first mark the water container, this line, top line. You can see the zoom in right here. That line is about, this is 40 millimeter, 45, 50 millimeter line. Then what we're going to do, click on the object submerge. As soon as it submerge, you can see water level rise. So what we need is the difference. How much difference happen in water level? Previous line, you have to remember the previous line. Okay, always previous line going to be same. Reset it, volume. Always starting point going to be 50 milliliters. Click on this. New line is about 60, 70 milliliters. Difference is about 20 milliliters, 70 minus 50. Now, milliliter is not the right unit we interested here, right? Because milliliter is not our unit at all. So we need what? Either millimeter cube or either centimeter cube or either meter cube for volume, right? So the conversion is very simple. So the conversion is each 1 milliliter. Conversion is very straight. Let me write it down that directly here. That might be useful later when you're doing the lab report. Each 1 milliliter is equal 1 cubic centimeter. That's the conversion, which means if the volume of the cylinder is 20 milliliters, so which mean that gonna be in 20 centimeters. So I can use 20 centimeter cube, and then the unit conversion is very straightforward and easy. Because of that, I'm going to use the unit centimeter cube directly without converting anything else at this point. Because always when we read, we like to report that as it is what we're reading, okay? All right, question. That's it then, so simple. You click on the next object, you know starting point always 50. It is 70, 75, which means difference is about 25. Very simple, 25. And then click on this tone. Starting point always about 50. This is on 75, which means difference is about 25. Okay, so we have everything done there. Now uncertainty of the volume, right? Let's take a look. What is the uncertainty of the volume? Now, what's the smallest number you can measure on this scale? If you take a look, the smallest number means this one of this is small line, right? Each of this small line is about like 5 milliliters, 60, 65, 70, 75, 80. So which means each of the line is 5 milliliters. Because of that, uncertainty of the measurement of that volume measurement is about half the least count, that about 2.5 in milliliters, which means I'm going to use a centimeter cube, which means always it's going to be about 2.5. Follow me? Centimeter, this should be cube, okay? Question. Okay, so seems to be fine. Then let's continue. So now we already have mass and volume. We have all the units and everything. All we need to do is to do the calculation for the density. That's very simple. You know density is mass of volume. So let's calculate equal sign. Mass of the object cylinder divided by volume of the object cylinder equal sign. If you do one calculation in Excel, if you click on that green solid dot on right hand side bottom and then click and drag, it will do the rest of the calculation automatically. However, you have to reformat this into right sig figs. I have 4 here in terms of significant figures. I have 1 here. Let me do one quick thing actually. If you do into 1, this is going to be very bad in terms of accuracy, right? This cylinder, I can't actually read anything more than that. That's really bad. So that's all really. I have to read into that accuracy, otherwise no meaning really. So no meaning adding anything. Oh, one thing we can do, sorry. Yeah, so that's what I was thinking. Now you can see the volume, when you do the volume measurement, you can have at least 1 decimal places because of the error, right? Uncertainty. Let's do that. So let's highlight, format. I should have at least 1 decimal place. That's good. Then our significant figure will be better. Okay, now it's good. Now if you go and take a look my calculated value here, mass has 4, volume has 3. I should have 3 here. Mass has 4, volume has 3. I should have 3 on both of these. 3 sig fig, format cell, number, 2 decimal places with the number. 3 sig fig, but the third one, this has 3, this has 3. I can still go 3 sig fig. All of these can have 3 sig figs without any problem. All good. Okay. We are on table number 9 now, okay? Question. Now let's take a look at the units. So the unit should be, I have mass, unit grams, divide by volume, cubic centimeters. So that's our unit. It's not the SI units, that's okay. Leave the unit as it is because later right here in table 10, you see it asking in SI units. Okay. And in table 10, you can see it not asking non-rounded value or anything. So because of that, we can keep the rounded value here. Okay. Those are the things you have to be vigilant and then keep it in mind, take a look what comes next. And then sometime we have to do certain adjustment accordingly. Okay. Now this is not asking any non-rounded value. So our rounded value here is fine. Question. Now that's very simple. Now let's take a look how to do the error calculation for this, right? Now what we done, we calculate the density. Density is actually ratio between 2 physical parameters, right? You remember 2 rules we're looking into when we're doing the propagation of errors. One rule, addition subtraction rule. Other one is multiplication division rule. Now this one is the ratio between 2 physical parameters. So which means I should take a look division rule. So don't need to remember any of those. Okay, all of those are on your lab manual, where in detail it's written. So you just go into lab manual and then take a look what physical parameters we're dividing, mass or volume. So which means technically I can use the division rule, right? So if you have the mass or volume, I should have a fractional mass to the power 2. Fractional error for the volume to the power 2 is square root of that multiplied by the density. So let's do that calculation. We are on table number 9. So it asking you to do separately fractional error for the mass, fractional error for the volume, then final the density error. Okay. So let's do fractional error. Fractional error means error of the mass divided by equal sign. Error of the mass divided by measured value of the mass. Hit enter button. If you want to do the same calculation for the rest, click and drag right hand side, solid green dot on the very bottom. Any questions so far? Now it's too many significant figures. That's okay. Leave it like that because that is not the final calculation. In between the calculation, we don't change the significant figures. Okay, we round the significant figures at the end. This is one of the end calculation. This is one of the end calculation because that's the error for density. But these two lines are not the end calculation. So I don't care the number of significant figure here. Just leave it like that. Let's do the fractional volume equal sign error for the volume divide by measured volume. Now you can see fractional error is fairly large number because the error for the volume is higher and also the volume measured is smaller, not much larger. Now you can see these two numbers doesn't have enough significance. So let's round it, highlight it, format it. Let's give more significant figure that is in between the calculation. Let's do 4 decimal places, one number. So it's not really much meaningful because these are 0, but still you have to show them, right? So that's important. Just leave it like that. Let's do the error calculation for density now. What's the error calculation for density now? Equal sign calculated density multiplied by SQRT square root parentheses fractional mass, fractional error for the mass power 2 plus fractional error for the volume power 2 close brackets. Now that is the error for the density. Now you can see that density error is fairly large number compared to this calculated value. The reason why it is larger, you can see these errors. The instrument we're using are actually have large error. That's a problem. Now if you doing this experiment in class, these numbers going to be extremely small. Let me show you one. So if you do this in class, usually our balance, the error going to be, uncertainty going to be about 0.005. See that number is changing accordingly, okay? And the volume uncertainty usually, if we measure this dimension by using the Vernier caliper or micrometer screw gauge, it's going to be about like 0.05 level. See that? Immediately, if you change those errors, uncertainty of the measured instrument, see that number now. So that's the problem with this lab, okay? We're not going to use those numbers. Please use the numbers we have. Because these uncertainties are large, your delta or the calculated uncertainty is going to be large value. That's okay. Just leave it like that. And I need the unit here. Unit going to be same as the calculated unit here. Let's do that here. Okay. Now this number is actually calculated value. I should round it, right? So let's round it. Let's highlight all of these three, round it to write significant figures, how much significant figures I can have. Now you have to take a look when I do that calculation, how many significant figures minimum I have right here. These two have only 2. Uncertainty of the mass and volume. So I can have only 2 sig fig for this case, one number and one number. One number and one decimal place. Let's calculate the rest. If you go into the previous cell, click on the right hand side very bottom green solid dot, downward direction. It will calculate it automatically for you the rest. Question. FNE F55, there's no formula. That's just a number. We got it by looking at the, that's a number we got by looking at the instrument. That's instrumental error. This is the instrumental error from the volume measurement. This is the instrumental error for the mass measurement. There's no formulas or anything. Let me copy paste this formula. This might be useful. Yeah, for this we'll copy paste that formula here. Let us copy paste into here. This will be now delta rho for the cylinder. Okay, delta rho for the cylinder. It's going to be same for the others technically. Okay, that's the equation for the delta rho for the cylinder. That is M55. Okay, this cell right here, M55. Okay, now it is same for the other tree, right? So if you want to do other tree, just click and drag. Now the one thing you have to take a look here. Now the locand is torn. You can see the error has only one sig fig. That is not good, right? So I have to reformat that. Right click, format cell. I can go 2 decimal places, then I can represent 2 sig fig correctly, okay? Because all of these should have 2 sig fig because these numbers has only 2. All right, now let's continue to the last table. So the last table, all we're gonna do is rewriting those. It's not really big deal at all. So let's rewrite that. So to rewrite what we're going to do here, I need to rewrite in a standard format, right? See the density plus or minus error calculated for the density in SI units. I don't have the SI units, that's okay. Let's convert the unit first to see what's the conversion means, right? Let's see that. So I have gram. So each 1 gram is equal about 10 to the power -3 kilogram, right? Question, those things you should know in generally, otherwise those are in our formula sheet, okay? And which mean I need to convert centimeters. Each 1 centimeter is equal 10 to the power -2 meters. But I need to convert centimeter cube, which means 1 centimeter cube is equal 10 to the power -6 meter cube. So that's the conversion. Now I have to convert gram divided by centimeter cube into kilogram divided by meter cube, right? So in kilogram, you have 10 to the -3. Centimeter, you have denominator 10 to the -6. Because of that 10 to the +3 goes to the numerator, this unit going to be kilogram per meter cube. So that's the unit conversion, okay? Question. Anybody have any problems with those? Those things generally you should know, otherwise nothing much to worry. Just as we moving on, make sure you learn them. Okay. Question. No questions. All right. So then let's take a look. What next? So the last table. So all we have to do now, we need to write it down, which means I have to just multiply this parameter, right? Let's go into here and then write it down here in our nice formatting with the equation editor and then bring that, okay? Parentheses, calculated cylinder density is 8.38, and then plus or minus, and then the error is 1.1, close brackets. So the unit now is gram divided by centimeter cube. I can do that by using this format nicely. That's going to be centimeter power cube. Okay, so now that is if I use in gram per centimeter cube. However, I'm interested in SI unit, which means I have to multiply that by 10 to the +3. Let's do that here. Equation. Bring this part again, and then let's do 10 to the power +3, and then I can use kilogram divide by meter cube. So that's our nice formatting. Question. Okay, now the one last thing we have to do now. By looking at this number, question asking you to predict the material. What type of material this cylinder made, right? Let's take a look. So what's the material is? So I know the density should be 8.38. So what we know about the density? Generally, density is a constant for the material, right? It's not going to change with the shape or the size of the material object. So all you have to do, go into your lab manual. So lab manual should have to have a table. Page number 7. You see that table? So that table is actually some of the non-material standard density values because it should be a constant. So let's take a look. Closest number to 8.38. So the brass is close by. Copper is 2 off, not good. And the brass is the only one which is close by. That's it. That should be brass. So let's bring that 8 point, what's the number? 8.44. So our predicted material is, you can say, brass. And the expected value of density in SI unit, so 8.44. But I have to write SI unit, so which means I'm going to copy paste this and then put it here because I need to use the nice formatting. Okay, that's why. So let's do now this number. I don't have error or anything. Okay, 8.44 times 10 to the power 3 kilogram per meter cube, because if you take a look the unit for that given in the table, that unit also given in gram per centimeter cube. Okay, that matches exactly the numbers we measured. Now, if you have a standard value I mentioned earlier, now these are the type of error you're going to do rest of this class. Most of the end of the classes, we're not going to do this propagation error, these calculation, right? These we're not gonna do in for every lab. One reason is that it's very difficult to do. It's very time consuming. So we're not going to really spend a lot of time on doing it. Those are important, but it's difficult with some of the lab. Actually, it's difficult to do at all. And also physics 2 class, physics 3 class, percentage error, something we're gonna do always. So which means if you have a standard value, you have to compare. That's called the percentage error. Let's compare this. Equal sign, ABS, parentheses, standard value 8.44, that's the expected value, minus what the value you got, 8.38, close bracket, divide by expected value 8.44, multiply by 100. Delete that extra space. Now let me copy paste that function too. So let me write here, that is the PE equation which I done for cell number G66. Okay, let me write it down, that cell number also here. Cell number G66. Okay, question. Now how many sig fig I can have here? Both numbers I am using have 3 sig fig, so I have to redo this. Format cell, numbers, format cell, numbers. I should do 3 decimal places because I should show 3 significant figures. That's all. Very simple calculation for this part of the lab. Not really anything serious except this function right here. Okay, and you can see the power of this calculation with this function, because if you do this with the calculator, there are so many errors happen and so many time consuming. So both of them can minimize if you do this way. Question. Okay, then let's take a look the other two objects. So other two objects, I already have the numbers, log 8.7, error is 0.88. All I have to do just copy paste this one and then edit. So let's edit this one. Only I need to edit these numbers, 8.70, and then error is 0.88. 0.88. And then let's go and take a look what that material is. I need the number close to 8.7. So let's check here what is the number close to 8.7. nickel close by, but this is not a nickel, because the reason, if you take a look at object, that's the lock, that is a yellow color. Yellowish color metal is usually a copper or the alloy of a copper. So you have to use other information known, just we can't read just blindly in our table, right? So if I use that information, copper we have 8.95 close by, but the 8.8 is more closer, but this is not the right number. Let's see any other numbers close by. No, so only these two. So I'm going to read the number 8.95. That's the copper, okay? Copper or the alloy of a copper, right? Both can be correct because it's a metal yellowish color. So this is going to be 8.95. Let's do the percentage error. Equal sign ABS, parentheses, expected 8.95. 8.95 minus calculated 8.7, close divide by expected 8.95 multiplied by 100. So that has a little bit of higher error than the previous, but is still in the range of acceptable error margin. Format cell, only 3 sig fig, which means one number and 2 decimals. Question. Okay, then let's continue to last one, stone. What's the number I have? 2.7.29. Let's copy paste this again and then edit that. 2.7 and then the error is about 0.29. 0.29. Okay. Let's go and check our table. What's the closest to 2.7? Aluminium is exactly, but this is not aluminium. See, those are the like the general ideas, general information you should follow. We can't really blindly read any numbers from the textbook. That's not going to help in terms of science, right? If you're searching something, you have to be very vigilant, very careful what we read. Now, why I'm not saying this is not aluminium, the reason, if you go and take a look, this is a stone, right? Aluminium is a metal piece. It's not a stone made of aluminium. If you look at that stone, there's no way that made of complete aluminium. That's impossible because aluminium is more white color. So even the aluminium oxide there, it can't be just black color. So because of that, we can rule out that number. Even though it's perfect match, we can rule out that. Let's take a look what next. Nothing here. It might be calcite. That's a possibility, but the color of the calcite is also not black. Let's take a look what other. Feldspar. So that's a good number, actually, 2.57. And let's continue. 2.12 too low. Talc 2.75. And let me tell you now, if you don't have the extra information, you have freedom of reading either calcite or either feldspar or either talc. Doesn't matter. But if we know more information, then we should go for that, right? So the other information is that if you do this lab in class, so the information we have is actually this name right here, feldspar, and the information related to feldspar will be given to you. So because of that, if I compare all of those and rule out in the color, the calcite and the talc is not possible, then I'm going to read into feldspar, okay? That one reason, assuming that extra information is given, okay? Otherwise, you have freedom to select actually any of those three if I don't have them. Only thing you can rule out directly without any extra information is the aluminium, because that must not be the case anyway. That's a pure metal. I'm going to read into feldspar, considering this is a in-class experiment, all the related information given. Because one other reason, then you have a little bit of high error there. If you're doing this in class, that's one thing it's going to be always happening. We will get fairly large error. So let's copy paste this. The standard value we expecting, let's say 2.59, 2.57. 0.7. Let's calculate the percentage error. Equal sign ABS, parentheses, expected 257 minus calculated 2.7 close bracket divide by 2.57 multiplied by 100. It's a little bit of large error. It is still acceptable. If you do this class, you're going to get much larger error than those. All right, guys. So that's everything about this lab. So only thing I left you to do these three, and then you have to do these two right here. And then other than that, we done everything. Any questions so far? Okay, then it's